Hello, dear listener, welcome. Settle in, find a comfortable position, and allow the gentle hush of the night to envelop you. Tonight, as the world outside quiets, we'll embark on a journey inward, into the very smallest, most fundamental building blocks of our universe. We'll explore a realm where intuition often gives way to wonder, and where the fabric of reality itself seems to shimmer with possibilities. Tonight we'll gently touch upon the profound and beautiful world of quantum mechanics. Quantum mechanics, just the name itself carries a certain whisper of mystery, doesn't it? It is, in essence, the fundamental physical theory that describes the behavior of matter and of light. Think of it as the deepest instruction manual for everything that exists. While the world we perceive with our senses, the world of trees and oceans, of stars and cities, seems solid and predictable, quantum mechanics reveals a hidden ballet, an intricate dance playing out at scales so tiny, they defy our everyday imagination. Its most unusual and truly mind-bending characteristics typically occur at and below the scale of atoms, those incredibly small units that make up absolutely everything around us and within us. This theory, dear listener, isn't just a niche area of physics, it is the very foundation upon which all of quantum physics rests. From the way chemicals react in quantum chemistry, to the intricate processes within living cells in quantum biology, to the theoretical frameworks of quantum field theory that describe fundamental forces, and even to the revolutionary advancements in quantum technology and quantum information science that promise to reshape our future. All of it sprouts from the fertile ground of quantum mechanics. It's truly a cornerstone, an essential lens through which we can hope to understand the universe at its most intimate level. Now you might be wondering, if quantum mechanics is so fundamental, why don't we encounter its strangeness in our daily lives? This brings us to a crucial distinction, the difference between classical physics and quantum physics. Classical physics, with its elegant laws laid down by brilliant minds like Newton and Maxwell, is wonderfully adept at describing so many aspects of nature at an ordinary, macroscopic scale, the scale of things we can see and touch, from a falling apple to the orbit of planets. It even works well for what we call the optical microscopic scale, allowing us to peer at cells and bacteria through conventional microscopes. But, and this is where the magic begins, classical physics simply isn't sufficient, it falls short, when we try to describe things at the very small, submicroscopic atomic and subatomic scales. Imagine, if you will, the gentle flow of a vast river. Classical physics helps us understand the river's current, the boat sailing upon it, the way a stone skips across its surface. But if we wanted to understand the individual water molecules, how they bond, how they behave when they collide, classical physics would begin to falter. This is where quantum mechanics steps in. It's the theory that delves into the individual molecules, the atoms, and the even tinier particles that compose them. In a beautiful testament to the interconnectedness of our understanding, classical mechanics can actually be derived from quantum mechanics. It emerges as a kind of approximation, a simplification that is perfectly valid at our ordinary, everyday scales. So, the world you experience every moment is not wrong, it's simply a large-scale, softened version of a much more intricate, probabilistic, and fundamentally quantum reality. Isn't that a comforting thought, that even the familiar is built upon such a deep and mysterious foundation? One of the most striking departures from our classical understanding lies in the very nature of quantities in the quantum realm. In our everyday world, we're used to measuring things continuously. Think of a car's speed, it can be 50 mph, or 50.1 miles per hour, or 50.0001 miles per hour. There's a continuous spectrum of possibilities. But in the quantum world, things are fundamentally different. Quantum systems have what we call bound states, like an electron orbiting an atom, and within these bound states, quantities such as energy, momentum, and angular momentum are not continuous. Instead, they are quantized to discrete values. Imagine climbing a ladder, where you can only rest your feet on specific rungs. You can't hover indefinitely between them. This is what quantization feels like. An electron in an atom can only possess specific, allowed energy levels, like steps on an energetic ladder. It can jump from one rung to another, absorbing or emitting a specific packet of energy, but it cannot exist in the space between those rungs. This is profoundly different from the continuous flow we observe in the macroscopic world, and it was one of the first clues that something truly revolutionary was unfolding at the atomic scale. As we delve deeper into this subtle world, we encounter another characteristic that gently tugs at our intuition: wave-particle duality. When we observe quantum systems, they show characteristics of both particles and waves. Now, in our classical minds, a particle is like a tiny, definite marble, a localized object. A wave, on the other hand, is spread out, like ripples on a pond. How can one entity be both at the same time? This is the beautiful paradox of wave-particle duality. Depending on how we set up our experiment, depending on what question we ask of reality, a quantum entity like a photon of light or an electron can manifest as a discrete particle or as a spread-out wave. It's as if the universe is telling us that our categories are too limiting, that reality at its deepest level transcends our simple definitions. And then, dear listener, we arrive at one of the most famous and philosophically rich concepts in quantum mechanics: the uncertainty principle. This principle tells us that there are fundamental limits to how accurately the value of a physical quantity can be predicted prior to its measurement, even if we have a complete set of initial conditions. It's not about the imprecision of our instruments, or our inability to gather enough information. No, this is an inherent property of reality itself. For instance, you simply cannot know both the precise position and the precise momentum of a particle at the exact same moment. If you try to pin down its position with great accuracy, your knowledge of its momentum becomes fuzzier, more uncertain. And conversely, if you precisely measure its momentum, its exact location becomes inherently blurry. It's as if the universe has a gentle secret, a veil it doesn't quite lift entirely, reminding us that there are intrinsic boundaries to what can be simultaneously known about the quantum realm. The journey into quantum mechanics arose gradually, a testament to humanity's persistent curiosity. It began with theories proposed to explain observations that simply could not be reconciled with the elegant, deterministic world of classical physics. Imagine the frustration, the intellectual itch, for scientists encountering phenomena that defied all known explanations. One such pivotal moment was Max Planck's solution in 1900 to the black-body radiation problem. He proposed, almost reluctantly, that energy was not emitted or absorbed continuously, but in discrete packets, which he called quanta. This was a radical idea, a whisper that energy itself was quantized. Then came Albert Einstein's groundbreaking 1905 paper, which built upon Planck's idea, explaining the photoelectric effect by suggesting that light itself was composed of discrete particles, or quanta, of light, which we now call photons. These early attempts to understand microscopic phenomena, often referred to as the old quantum theory, were like tentative steps into a new world, a new way of seeing. They were brilliant but incomplete. It wasn't until the mid-1920s that the full development of modern quantum mechanics blossomed, thanks to the collective genius of minds like Niels Bohr, Erwin Schrödinger, Werner Heisenberg, Max Born, Paul Dirac, and many others. They wove together these initial insights with profound mathematical formalisms, creating the robust and predictive theory we have today. In one of these specially developed mathematical formalisms, a mathematical entity called the wave function was introduced. Imagine the wave function as a complex, mathematical map that doesn't tell you exactly where a particle is, but rather provides information, in the form of probability amplitudes, about what measurements of a particle's energy, momentum, and other physical properties may yield. It's a map of possibilities, a blueprint of potential realities. Now, let's take a moment to understand just how profoundly powerful and yet philosophically challenging this theory is. Quantum mechanics allows for the precise calculation of properties and behavior of physical systems. As we mentioned, it is typically applied to microscopic systems, the delicate dance of molecules, the intricate structure of atoms, and the ephemeral existence of subatomic particles. And its predictions have been demonstrated to hold true, even for incredibly complex molecules with thousands of atoms. Think of a protein molecule, a vast arrangement of atoms working in concert. Quantum mechanics can describe its behavior. Yet, as we scale up, the application of quantum mechanics to objects like human beings raises fascinating philosophical problems. One famous thought experiment is known as Wigner's Friend, which delves into the role of consciousness and observation in collapsing quantum states. We won't dive too deeply into the specifics of Wigner's Friend right now, but simply appreciate that it highlights the profound questions that arise when we try to apply the rules of the very small to the world of our everyday experience, especially where consciousness might be involved. And its application to the universe as a whole remains, for now, largely speculative, though immensely intriguing. Despite these philosophical intricacies, the predictive power of quantum mechanics is staggering. Its predictions have been verified experimentally to an extremely high degree of accuracy. Consider, for example, the refinement of quantum mechanics that describes the interaction of light and matter, a theory known as quantum electrodynamics, or QED. QED has been shown to agree with experiment to within an astonishing 1 part in 10 to the power of 12 when predicting the magnetic properties of an electron. Think about that for a moment. 1 part in a trillion. It's a level of precision that is almost unfathomable, a testament to the profound truth embedded within this strange theory. It tells us that despite its counterintuitive nature, quantum mechanics is not just a philosophical construct. It is a description of reality that is rigorously tested and proven to be astonishingly accurate. A fundamental feature of quantum mechanics, and one that often causes our classical minds to pause, is that it usually cannot predict with certainty what will happen. Instead, it only gives probabilities. Imagine rolling a very unusual die, where you know the probabilities of each face landing up, but you can never predict with absolute certainty which face it will be on any given roll. Mathematically, this probability is found by taking the square of the absolute value of a complex number, a number known as a probability amplitude. This crucial mathematical rule is known as the Born rule, named after physicist Max Born. Let's gently consider an example, a quantum particle like an electron. Before we observe it, its state can be described by a wave function, which we touched upon earlier. This wave function associates to each point in space a probability amplitude. Now, when we apply the Born rule to these amplitudes, it gives us a probability density function for the position that the electron will be found to have when an experiment is performed to measure it. What does this mean? It means that the theory can tell you the likelihood of finding the electron at a particular spot, but it cannot say for certain where the electron will be found. This is the best the theory can do. It cannot guarantee a precise outcome for a single measurement. It speaks in the language of likelihoods, of tendencies, rather than certainties. The famous Schrödinger equation, another cornerstone of quantum mechanics, beautifully relates the collection of probability amplitudes that pertain to one moment of time to the collection of probability amplitudes that pertain to another, allowing us to see how these possibilities evolve over time. One profound consequence of the mathematical rules of quantum mechanics is a fundamental trade-off in predictability between certain measurable quantities. This is essentially the heart of the uncertainty principle we briefly mentioned earlier, but let's explore it a little more deeply. The most famous form of this principle, formulated by Werner Heisenberg, states that no matter how carefully a quantum particle is prepared, or how meticulously experiments upon it are arranged, it is impossible to have a precise prediction for a measurement of its position and also at the same time for a measurement of its momentum. Think of it like this. Trying to measure a particle's position with absolute precision is like trying to pinpoint a specific ripple in a pond. To do so, you have to interact with it, perhaps by shining a light on it. But this interaction, this shining of light, which itself is made of photons, quantum particles, imparts energy and momentum to the particle, thereby changing its momentum in an unpredictable way. Conversely, if you try to precisely measure its momentum, you essentially allow it to be delocalized in space, making its position uncertain. It's not a flaw in our instruments, it's an intrinsic feature of the quantum world itself. The universe, at its most fundamental level, has a built-in fuzziness, a certain indefinability when it comes to knowing these pairs of properties simultaneously. This isn't just a scientific statement. It's a philosophical one, reminding us of the limits of absolute knowledge and the active role the act of observation plays in shaping what we perceive as reality. Another truly captivating consequence of the mathematical rules of quantum mechanics is the phenomenon of quantum interference. This is often illustrated with one of the most iconic and mind-bending experiments in all of physics, the double-slit experiment. Imagine a coherent light source, perhaps a laser beam, shining towards a plate that has been pierced by two very narrow, parallel slits. Behind this plate, there's a screen where we observe the light that passes through the slits. Now, if light were purely classical particles, like tiny marbles, we would expect to see two bright bands on the screen, directly corresponding to the two slits. The marbles would go through one slit or the other, creating two distinct piles on the screen. Simple, predictable. But because of the wave nature of light, something extraordinary happens. The light waves passing through the two slits interfere with each other. Where the crests of the waves meet, they reinforce each other, creating bright bands. Where a crest meets a trough, they cancel each other out, creating dark bands. The result is not two simple bands, but a complex pattern of alternating bright and dark bands, an interference pattern. This is precisely what we would expect from waves, like ripples in water passing through two openings. The truly astonishing part, the part that opens up a universe of quantum weirdness, is what happens when we conduct this experiment not with a continuous beam of light, but by sending individual particles, one photon, or one electron, at a time. If we fire single electrons, one after another, through the double slits, something remarkable occurs. Initially, with just a few electrons, you might see individual dots scattered on the screen, seemingly random. But over time, as more and more electrons accumulate, they collectively build up the exact same interference pattern, the alternating bright and dark bands, as if each individual electron somehow knew about the presence of both slits and interfered with itself. How can a single electron, a tiny particle, pass through two slits simultaneously and interfere with itself? It doesn't make sense in our classical world. It's as if the particle exists as a probability wave, exploring all possible paths, until it finally hits the screen. But the enigma deepens. If we try to watch which slit the electron goes through, perhaps by placing a detector at each slit, the interference pattern vanishes. As soon as we try to determine the particle's path, it behaves like a classical particle, going through one slit or the other, and the interference pattern collapses into those two simple bands we would expect from marbles. This is the famous observer effect, or more accurately, the measurement problem. The act of measurement, the very act of trying to gain information about a quantum system, fundamentally changes its behavior. It's as if the quantum world refuses to be neatly categorized until we insist on an answer. Until measured, the particle exists in a superposition, simultaneously traversing both paths, a wave of possibilities. But upon observation, its wave function collapses, and it is forced to choose a definite state, a definite path. This double-slit experiment is not just a scientific curiosity, it is a profound philosophical statement. It challenges our fundamental understanding of reality. Does reality exist in a definite state even when unobserved? Does consciousness, or simply the act of measurement, play a role in shaping reality? These are questions that continue to inspire and perplex scientists and philosophers alike. It suggests that the universe, at its most fundamental level, is not simply there, waiting to be discovered, but rather something that emerges in part through our interaction with it. Dear listener, we have gently journeyed through some of the most profound concepts in quantum mechanics, its fundamental nature, its departure from classical physics, the quantization of energy, the baffling wave-particle duality, the intrinsic limits of the uncertainty principle, and the mesmerizing mystery of quantum interference. We've seen how this theory arose from whispers of the universe, how it was built by brilliant minds, and how its predictions have been verified with astonishing accuracy. Quantum mechanics invites us to embrace a world where certainty gives way to probability, where particles can be waves, and where the act of observation might just be a co-creator of reality. It's a world that is less about solid objects and more about shimmering possibilities. It's a reminder that beneath the calm, predictable surface of our everyday lives, there is an intricate, dynamic, and wonderfully strange quantum ballet playing out, giving rise to everything we know and experience. As you drift towards sleep, perhaps you can carry with you a sense of wonder at this beautiful, mysterious universe. A universe that, at its deepest level, is far stranger and more magnificent than we could ever intuitively imagine. Let the thought of these quantum whispers, these probabilities and possibilities, gently lull you into a restful slumber. May your dreams be filled with the quiet elegance of the cosmos, knowing that even in sleep, you are a part of this grand quantum dance. Sweet dreams, dear listener. Until next time.